Hello and welcome back to another episode of Math with Stone. Today we are going to be learning about torque. And torque is the measure of the force that makes an object rotate. So essentially, how hard you have to push something that's spinning around to get it to go faster or to slow it down or vice versa. So torque depends both on the magnitude of the force and the distance from the axis of rotation, which we're going to go into detail in a moment about. So essentially, you could have this pivot point. And if you apply a force downward perfectly perpendicular, then the torque would just equal the amount of force times the radius of however far away your force was. If you go closer to it, then your radius would shrink. Okay, so it's not necessarily the radius of the full arm of the wrench. It would be wherever you're applying the force that would be considered the radius here. Okay, so if you go closer, your radius would get smaller. Now, another scenario that you could have, which would require a different formula, would be this torque is equal to force times radius sine theta. So if you have a scenario like this where your amount of force is provided at an angle, then you would have to utilize a different formula, which I'm going to explain real quick to you why that is so. So if you have a pivot point right here, and we apply a force downward like that at this angle, how much of that is perpendicular? Well, if we go across from this, we would have our opposite side, and then here would be our hypotenuse, which is the actual force or magnitude. And remember that sine of the angle is equal to opposite over hypotenuse. Well, if you multiply by hypotenuse, you end up with hypotenuse times the sine of the angle, and that would give you your opposite side, which is perpendicular to the actual lever bar and will be the part that we would need because we only want the force perpendicular to it. So that is why we have hypotenuse sine theta, which is the force times sine of theta, and then the radius is thrown in the middle. Okay? So that's all that means. Now, the path of torque is defined as a vector. All right? The fact that it is a vector indicates that the direction matters, and because the direction matters, here you'll see that we have two different things. We got counterclockwise and we got clockwise. Counterclockwise is considered positive and clockwise is considered negative. And if you think of it from like a trigonometry perspective, if you go around backwards, like normal trig or pre-calculus, that is the positive direction for angle, and then the other direction, the clockwise, is considered a negative direction for angle. So it mimics that. Okay? So all that in mind, I want to show you what is torque in relationship to something real world. So torque, if you're turning a wrench, here you got the hand pulling the object around it, and it would be turning that bolt. And the torque is that rotational force. And the direction of that rotational force, I don't know if you can see it, is pointing upward, okay? Or downward, depending on the which way you are actually rotating that wrench. All right, so it's important to recognize that the torque is actually up or down. So the question you may be asking is, how do you know if the torque's direction is actually up or down? It is the force that is causing that rotation and so on and so forth, but how do you know if it's actually going up or down? You can be doing by something called the right-hand rule. And the right-hand rule indicates that if you curve your fingers, I'm going to zoom out and show you what happens, but if you curve your fingers, the direction that it is turning, see how it's turning to like this right direction? If you curve your fingers in that direction, the way your thumb points is the direction of the torque, okay? So let's zoom out, let's look at my hand. If we are turning counterclockwise, like I am here, counterclockwise, the direction of the torque is going to be through my thumb, which is going out through the top of the camera. It's going out from the page. Versus if we were to go clockwise with your right hand, not your left hand, if we were to go clockwise, you would have to like, notice how my thumb is not visible, and it would be kind of going down into the table if I'm going clockwise. Versus if I were to go like something to where you could visually see, you know, turned sideways, you can see where your thumb just kind of turns all over. So make sure you limber up whenever you're doing torque examples because you could definitely pull your wrist or something. Now, another thing that matters is, got to zoom back in, torque is related to distance. I briefly talked about it. the further away you are from the center or the pivot point, the greater the torque. And that is something that a lot of times people in mechanics know this a lot, because in order to loosen the lug nuts on your car, they actually use a really long wrench versus a really short wrench to do that. The units for torque is in Newton meters, which is the same thing as work, but it is no relationship to work. It is just called Newton meters. It's not a joule. It has no relationship, and therefore you should not do it. Don't think of it that way, but if you're trying to make the connection with work, it does not relate to work at all. A simple experiment you can do at home with these blurry doors that you have, if you're trying to open and or close a door at home, if you are really close to the hinges, it makes it a lot harder to actually close, and it makes that force required to accomplish the torque needed really difficult. And if you go really far away, if you're all the way at the handle, it's kind of easy to close the door. All right. Few other things that we need to talk about. Some things that will not cause torque. If you have your lever right here, if you apply a force down, that would create torque. Yes. If you have your lever and you apply your force right here, directly, like completely parallel with the lever, that causes no torque. No torque. Same thing as if we were to go over here. That would also cause no torque. It has to be applied somehow in some way, upwards or downwards on the pivot bar. And it also will apply no torque if you have the point of pivot. Let's say we have a bar. If we went up or if we went down on that point of pivoting, if it is either going up or down, there would be no torque either. All right? Something a little more rare, but it does, I do say it every once in a while, is you can have canceling actions. Okay, so if you were pushing down at a force of 50 newtons here and you were pushing up at a force of 50 newtons there, they're going to cancel each other out. Now, if you were to kind of change it, and this is getting into the next video a little bit, if you went down by 50 newtons here and you went up by 50 newtons a little bit further away, that would have some sort of torque because this 50 newtons is further away than this one, and therefore it would actually it would win, so to speak. It would win the battle. All right. Let's do a quick example before we get moving on and being done for the day. So let's say here we got an example. We got Bob the Builder. He uses a wrench to tighten a bolt, as shown. He applies a force of 17 newtons, and it is 25 centimeters away from the bolt at an angle of 37 degrees from the axis of rotation. Here's the diagram. The only thing difficult about this problem is the fact that it is in centimeters. You will have to turn that into meters. You got to turn it into meters. So 25 centimeters is 0.25 meters. In case you were wondering, you could divide by 100. And then you just use your formula. Torque is equal to force times the radius times sine of theta. Make sure the angle is with the wrench, not over here. Okay, so sometimes you'll get the angle over here where I put that arrow. You don't want that angle. You want where the angle is in this case, which is 37. So our torque is going to equal our force, which was 17 newtons times 25 centimeters times sine of 37 degrees. So we got 17 newtons times the 0.25 meters times sine of 37 degrees. If you do all that, make sure your calculator is in degree mode. You end up with 2.6 Newton meters for your torque. Okay? So that's going to do it for this one. Until next time, I will see everybody later. Stay positive, my friends. Bye.